All right, let's get started. Good morning. Okay, so we came up a short on our Relay for Life fundraising goal, so I'm still in normal clothes today. But it was still good effort. We raised a good amount for Relay for Life. Once again, it's a very, very good cause. It goes to cancer research, treatment, and prevention, and finally a cure eventually. So thank you very much for participating, and thank you for your contribution to that wonderful cause. All right, so today we're going to be looking at the second part of section 4.3. We're going to continue our focus on derivatives and how they affect the shapes of graphs. So first of all, a quick summary from last time. We saw that if f prime is positive, then the function f is increasing. If f prime is negative, then the function is decreasing. We also remember that if the function was increasing before and decreasing after, then somewhere in the middle we reached a relative maximum. Relative or local max. Happens when f prime changes from positive to negative, increasing before, decreasing after. So the flat point in between must be the maximum. And conversely, if the function was decreasing before and increasing after, then we've reached a local minimum at some point. Okay, then we look at what happens with the second derivative. We saw that f double prime positive tells us that's when the function f is concave up. And if f double prime is negative, then the function is concave downward. And finally, if f double prime changes sign at some point, plus to minus or negative to positive, doesn't matter, then we have what's called an inflection point. Okay, so all of this stuff is what we saw last time. We look at increasing, decreasing, local max and min, the shapes of the graph based on the second derivative, and the inflection point. Now we're going to look at the second derivative in a little bit more detail. If f double prime is positive, we know it's concave upward. It also means that f prime of prime is positive. Okay, so this tells us that when the graph is concave upward, it is also when the slope of tangent line is increasing. Therefore, if you're given a graph of f prime, you look for when f prime is increasing. That can tell you the interval on which f would be concave upward, even if you don't have the graph of f. Conversely, if f double prime is negative, then f prime prime is less than 0. So this tells us that f is concave downward. On the interval when f prime is decreasing. Decreasing tangent line slope on the interval means the graph is concave downward. Increasing tangent line slope on an interval means the graph is concave upward. Okay, we also saw last time that when f double prime changes signs from positive to negative or negative to positive, we have inflection point. So let's consider what happens when f double prime, f prime prime goes from plus to minus. Two things happen. First, remember, when the derivative of something goes from plus to minus, that means that something has reached a maximum. This means that f prime has a local maximum. It also means that f itself has an inflection point because f double prime has changed sign. Okay? So on the graph of f prime, if you see a local maximum, that's when the graph f, the original function I gave you, that derivative, has an inflection point. Same thing here. If f prime prime goes from negative to positive, then what this means is that f prime was decreasing before, increasing after. So f prime has a local minimum. It also means, just like in the case above, f has an inflection point. Okay, so all this is just based on reasoning of what we know from last time. Whenever the derivative of something changes sign, we have a max or a min. In the case of the first derivative, that means whenever the first derivative has a local max or min, that means on the original function we have inflection point. All right, does that make sense? Question? Inflection point occurs whenever f double prime has a sign change. If you're given the function, you take the second derivative, find out where the sign changes. Kind of like how we find the critical numbers with the first derivative. Look at the example we did at the end of last class, where we actually went and found an inflection point. Other questions? Okay, so let's keep this in mind here and do this example. So here I'm sketching the graph of f prime, the derivative of something. And I'm going to make it look like just part of a sine curve again. And let's say that's 4, 2, 6, and 8. We would like to know on what intervals is the function f, the original function, the function that gave us this derivative, which we don't have. But even just with the information here and what we saw on the last page, we should be able to determine the intervals on which the original function f is concave up or downward. And if we know that, we also know where the inflection points are. Okay, so look at the last page here. We found out that using the information we already know, the function itself is concave up when f double prime is positive. That also means when f prime prime is positive. So that happens when f prime is increasing. I'll write down what I just said. Okay, concave upward, what happens whenever f prime is increasing. Now, based on the graph of f prime here, give me the increasing intervals. On what intervals is f prime here increasing? Right, yep, 0 to 2, 6 to 8, right? So f prime is increasing on the two intervals 0 to 2 and 6 to 8. On those intervals, f prime prime is positive. So on the original graph, which we don't have, and we don't need it actually, we know the function would be concave upward, taking the shape of something that looks like an upward opening parabola on the intervals 0 to 2 and 6 to 8. The original function f, whose graph we don't have but we don't need, is concave downward if f double prime is less than 0. That means f prime prime is less than 0. And that means f prime is decreasing. Okay, then we stare at the graph of f prime, find out on what intervals it is decreasing. And we only have one. From 2 to 6, f prime is decreasing. Therefore, on 2 to 6, the function that gave us this derivative must also be concave downward. Okay, any question on those intervals we just found? Okay, good. The inflection points on the function f. Okay, inflection points happens when f double prime changes sign. That means the slope on f prime is changing sign. That means f prime itself would have local maximum or local minimum. So here you simply look at where the local max and min for the function, for the derivative is, 2 and 6. Those will correspond to the inflection points of the function that gave us that derivative. So here f will have inflection points at x is equal to 2 and x is equal to 6. Okay, any question on this one? Okay, let's do another one like that. Once again, we're going to start with the graph of f prime. And let me sketch that. I want this to look like this. I want this here to occur at 2, 1, 3, 4, 5, 6, 7, 8. Very simple. Okay, just like that last example, we want to use the graph of f prime, which we have, to determine on the intervals on which the function, the original function that gave us this derivative, is concave or upward or downward. We also want to find out where possible inflection points are. All right, you got 3 minutes to try this. Very similar to what we just did. So try this for 3 minutes. actually add this too. In addition to that, also find out where the function that gave us this derivative is increasing or decreasing. Yeah. It's going down to negative infinity. It's not coming back again, it's just going down. Assume this just carries on forever. All right, that's close enough to 3. So let's start with this one actually, the increasing and decreasing. Okay, so on what intervals is the function f increasing? And how did you know that? Right, exactly. 0 to 4, 6 to 8, right? F prime is positive on 0 to 4, 6 to 8. Good. Any question on that? All right, so F is, I'll just write it. Decreasing, well that's simple. Wherever F prime is negative, 4 to 6 and 8 to infinity. Does the function f have local max and min? Let's write that too. Where would the function, the original function, have a local maximum? It happens when f goes from positive to negative, right? So that occurs at 4 and 8. Right? F goes from positive to negative. F prime goes from positive to negative here and here. What about 6? What's going on here? I didn't catch that. Min, okay. Local min at x is equal to 6. What about intervals where f is concave upward? Which intervals? Zero to 1, 2 to 3, 5 to 7. Do we agree with that? Yes? No? Don't care? That's not acceptable. So who agrees with that? 0 to 1, 2 to 3, and 5 to 7. Sounds good? good. And we know that because that's the interval, those are the intervals on which f prime is increasing. Therefore, f double prime is positive. So it's concave down on the intervals where f prime is decreasing. That looks like 1 to 2, 3 to 5, and 7 to infinity. Sounds good? One to 2, 3 to 5, and then 7 to infinity. How many inflection points does f have? Several. Okay, good. Be more precise. And where are they? Yeah, those are the local max and min of f prime, right? You look for them. We have 1, we have 2, 3, 5, 7. Okay? Any question on any of this stuff on this example? Okay, good. Now, if you have no trouble with that, you should be able to answer this old exam question then. So you got 2 minutes. 2 minutes. All right, that's 2 minutes. What do you think? C? All right, let's go through these one at a time. Statement 1, f has a local minimum at x is equal to 3. So at here, we have f prime positive before, f prime negative after. So f has a local maximum, right? So right here, f has local max. So that one is not right. Statement 2, concave upward on 1 to 2. 1 to 2. And we can see that on this interval, f prime is increasing. So f double prime is positive. So that's a true statement. Okay, I'll write it this way. This is false. This is true. And the last one, f is increasing on the interval 0 to 3. Well, that looks pretty clear. 0 to 3, the entire f prime is above the x-axis. So that's true. So you're right. Very good. 2 to 3. Right? That's an easy problem that everyone should be able to get. Okay, any question on this one? All right, so now we're going to look at the second derivative a little bit more and see what it can tell us about local max and min of the function f. Imagine we have this kind of graph for f, the original function f. And I want it to look like this. All right, so looking at the original function, not the derivative anymore. And I want this to be at 1, 2, 3, and 4. So look at the local maximum and minimum of this function. At 1 here, we have a local minimum. We know this occurs just by looking at the graph f prime is equal to 0. We know that's a necessary condition as a 0 flat tangent line. Now also look at the shape of the graph near the local minimum. So I'm going to kind of make that part a little bolder, kind of like this. Our local minimum is sitting near a region that looks kind of like part of a parabola that opens upward. And we know when that happens, the second derivative is positive. It's concave upward near the region of the local minimum. See that? And notice the other kind of thing happens at local max. At the local maximum at x is equal to 3, again, f prime is equal to 0. This time it is sitting on the top of a downward opening parabolic shape. It is concave downward. So f double prime is less than 0. Okay, so this is telling us that if we can find the critical numbers and if we can find out what the sign of the second derivative is at the critical numbers, that's another way for us to tell whether we have a local max or a local min. And this is called a second derivative test. And the test says if x is equal to c is a critical number of the function f of x. And remember, that means f prime of c is equal to 0 or f prime of c is undefined. Finding this tells us where the flat tangent lines are or where the tangent lines don't exist when we have a cusp or a corner. So this tells us where these two things are. And once we found those, we use the second derivative to tell us what the local shape may look like. If f double prime of c is positive, this kind of thing here. If at the critical number, the second derivative is positive, concave up, then we know there is a local minimum at x is equal to c. That tells us we're sitting at a concave upward region, so we must be at a local minimum. If f double prime of c is less than 0, then we got this situation. Then there is a local maximum at x is equal to c. Negative second derivative, local maximum. We get into a little bit of a trouble if f double prime of c is exactly equal to 0. If that happens, then we can't tell from this particular test. That location could still be a local maximum or minimum, but we can't tell from this test. And when that happens, you'll go back to the first derivative test that we learned last time to look at the slope before and after each one. All right, so this one is convenient in the sense that you only need to check couple things by using the second derivative. If the second derivative is easy to find, this is usually a better, faster test. You're just plugging 1 or 2 numbers or 3 into the second derivative. If the second derivative is hard to find, you may want to consider the first derivative test that we used last time. Example. X to the fourth minus 4x to the third plus 1. That's 4. And then let's use the new test we just learned. Let's find out where the critical numbers are. Regardless of which test you use, you have to find the critical numbers no matter what. So we take one derivative, we look for where this is equal to 0. We can take out a 4x squared from that. And this tells us that we will have f prime equal to 0 at x is equal to 0 and x is equal to 3. And each of these could potentially be a local maximum or local minimum. They don't have to be either. It could be a point that's just a brief pause without becoming a local max or min. We'll find out once we use the test. And by the way, f prime does not exist. It's not going to happen. because f prime is a polynomial. Right? 4x cubed minus 12x squared. Polynomial is always defined for any value of x. So the only two critical numbers we get are 0 and 3. Okay, now we use the second derivative at these two locations to tell us what's going on. Let's take one more derivative. We plug in these two into f double prime one at a time to see what's going on. At 0, f double prime is 0. So here we have the last of the possibility we listed on the last page. When the second derivative is exactly equal to 0, we don't know what's going on. So for now, all we can say is that the test is inconclusive for this one. We'll have to come back to it. We still need to find out what it's doing here, but let's find out what 3 is before we tackle that again. Now we take 3, plug into here. All we care is the sign of that number. The number itself doesn't mean much for this purpose. Here we have 12 times 9 minus 24 times 3. That's clearly a positive number. And according to what we saw on the last page, this tells us that we're sitting at a flat region and the neighborhood is concave upward. You're on the concave upward at a flat region. You must be sitting at the local minimum. Okay, so we know what's going on here, and we've got to go back to 0. For x is equal to 0, let's use the first derivative test. And we're only doing that because we couldn't find a conclusive answer for that. If both of these turn out to be something that we could draw a conclusion on, then we're done. The only reason we're doing this is a backup. Okay, remember what we did. First we put the line and we put down the critical numbers. And then above the line we check the sign of f prime, right? We know what's going on here, so we don't really have to pay much attention to that. We only want to know what's happening at 0. Now be very careful. The sign, we're looking for the sign of f prime. You have 3 things here. You got to be careful what they do and when to use them. The original function is you use that to find out the y value that goes with this one, for example. F prime tells you the slope. That's why you use it for the first derivative test. F double prime tells you the shape. That's what the second test would need. Okay, so let's find out what's going on. If I choose a negative number here, it helps if you look at the factored form. If I choose a negative number, this is positive no matter what. And if I choose a negative number, this is negative. So I know I'm going to have decreasing interval on that interval. The function will be decreasing because f prime is always negative. If I choose x is equal to 1 here, once again, the factored form is convenient. That's always positive. If I choose 1, that's clearly also negative. So now we see that because there's no sign change, the function was decreasing before, decreasing after. Therefore, x is equal to 0 is not a local max or a min. So x is equal to 0 is not local max or local minimum. It's just a very brief stop. The thing was decreasing before, come to a momentary stop, and decreasing after. Like I said last time, it's like when you take the stairs down from the third floor back to the ground floor. When you get to the second floor, you come to a brief stop, and then you continue going back down. That's what's going on here. 3 to 2, stop. 2 to 1, and then you're out. Okay, let me show you again what exactly is going on with this x is equal to 0. When f double prime is 0, sorry. We're going to consider a very, very simple function. X to the 4th. If I take the first derivative, make that equal to 0, I see x is equal to 0 is a critical number, right? So there's potentially a local max or min at there. But knowing the geometric shape of that, we already know it's a local minimum. Notice what's going on with the second derivative. And here we run into, again, a test being inconclusive for that one point. Take a look at the graph. If you have x to an even power, any even power, you always get a parabolic shape. X squared is a standard parabola. X to the 4th will look a lot like that, but it gets wider and wider, and the bottom gets flatter. So this will get something that looks kind of like that. And for x to the 6th, x to the 8th, the same shape will be kept, but the bottom here gets more and more flat. So for example, x to the 100th, for example, is going to look like this. Very, very flat down here. It'll look almost like a rectangle. If you graph this x to the 100th power, you see essentially kind of a rectangle thing. And this is the reason why f double prime is 0. So first of all, we know from graph, we see a local minimum at x is equal to 0. But because it is near a very flat region, it turns out that it's not actually concave upward or downward near that region from f double prime here. It's actually incredibly flat. So even though it is a local minimum, just because we know what the graph looks like, same thing with x to the 100th, we know it's a local minimum. But the geometry of the graph is not helping us. We actually get f double prime is equal to 0. So on the last example, we found out where f double prime is 0. It turned out to be nothing significant. But this can happen too. You could have a region where f double prime is 0 and still be either a local max or local min. So it's always important to check when f double prime equal to 0 shows up. It could be anything. Okay, that's it for today. See you Wednesday.
say that it's worthwhile going to even older tests? Because it looks like the curriculum has changed. Like the further I go back.
Yeah, it changed a little bit, not dramatically. And so that change occurred in the spring of 2016. So anything prior to that, it'll look a little bit unfamiliar here and there. But the big picture should still be applicable. So it is still a good exercise to do. But you might want to focus on the more recent ones. But if you don't think 2 or 3